Welcome back. We continue looking at the power function and the operating characteristic function, and we'll do so through some examples. So let's first consider the test. It's a right-tailed test, the null hypothesis of which is that the mean of the population is less than or equal to 100 against the alternative hypothesis that the mean is greater than 100. And the population standard deviation is equal to 5. Now the test will be performed using a significance level of 0.05, so it's a 5% significance level, and the sample size that we'll use is 25 observations selected at random from the population. Now for each value of mu given below, we want to compute the power of the test and also beta, the probability of committing a type 2 error. So for mu equal to 100.5, mu equal to 101, and mu equal to 102. Now notice that each of these values is consistent with the alternative hypothesis, which says that mu is greater than 100. And so if any of these situations is the actual state of nature, then the alternative hypothesis is true. And so what we want to do is to see how much power we will have in detecting the fact that the alternative hypothesis is true for each of these three scenarios. All right, so let's first consider the possibility or the situation where the population mean is equal to 100.5. And by the way, notice that since we are using a 0.05 level of significance, for this right-tailed test, the critical point is positive 1.645. Now, if mu is equal to 100.5, then at that particular value of mu, the power of the test, which is denoted using this notation, so the pi symbol, lowercase pi, so the power of the test when mu is equal to 100.5, this can be represented in a couple ways, as we've indicated in the previous lecture. So the first way that we could represent this is that it's equal to, or given by, the probability that z-calc, the test statistic, is greater than the critical point, 1.645. But this particular representation, and especially when we're doing this by hand, really does not show how mu is a part of this computation. But remember that when the alternative hypothesis is true, then z-calc no longer has a standard normal distribution. It has a normal distribution with a mean equal to mu minus mu sub 0 over sigma divided by the square root of the sample size. And so the mean of the sampling distribution of z-calc is where mu comes in. But it's not at all obvious from this particular representation. We just have to remember that. But now another representation for the power is expressed in terms of the standard normal random variable z instead of z-calc. And with that representation, then we see where mu comes into play. 100.5 is given right here. From that we subtract the hypothesized value of mu, or more correctly stated, the boundary of the null hypothesis space, which is 100, and then we divide that difference by the standard error of x bar, which is sigma over the square root of the sample size. In this case, sigma is equal to 5. The sample size, you'll recall, is 25. And so we can see, just doing a quick mental calculation, that the denominator is going to be 1. All right. And so then when we carry out that calculation, we see that the power of the test when mu is equal to 100.5 is equal to or given by the probability that the standard normal random variable is greater than 1.145. Now we're going to be determining this probability, at least an approximation of that probability for now using the standard normal table. And so using the standard normal table that's available on the course Moodle, all right, we want the probability that the standard normal random variable z is greater than 1.145. Now notice that this is in fact a right-tailed table, all right? And so what we want to do is look for 1.145. But now what we see here is that the z values are not given to 3 decimal places, they're only given to 2 decimal places. And so we're not going to find 1.145 in the table, all right? But we do see 1.14 and 1.15. And so we know that the probability we're after is going to be somewhere between 0.12507 and 0.12714. Now, it's often going to be satisfactory to round the z value that we have to look up to 2 decimal places so that it matches the precision of the z values given in the table. All right, and so for right now, that's what we're going to do. All right, we're going to round the 1.145 to 2 decimal places, and so that gives us 1.15. And so that will be the value that we use for this probability. We realize that it's an approximation, all right, but it's for now going to be adequate. So how much power do we have for detecting the fact that the null hypothesis is false and the alternative hypothesis is true when mu is equal to 100.5? Now remember that the null hypothesis is that mu is less than or equal to 100, and the alternative is that mu is greater than 100. So if mu is equal to 100.5, then the alternative hypothesis is the true situation, but it's just barely true, right? Mu is not that far into the alternative hypothesis space. And because of that, we see that we don't have much power for detecting the fact that the null hypothesis is false. In fact, there's only about a 12.5% chance when mu is equal to 100.5. There's only about a 12.5% chance that we would get a hold of a sample that would lead us to the correct conclusion that the null hypothesis is in fact not true and that the alternative hypothesis is true. There's a very high probability, approximately 0.87497, or about 80. There's about an 87.5% chance that we would get a hold of a sample that would lead us to conclude that the null hypothesis is true. Okay, so we see here that when mu is not that far into the alternative hypothesis space, we have very low power and a very high probability of committing a type 2 error. Now let's move into the alternative hypothesis space a little further than mu is going to be a little further away from 100 in this particular situation. All right, so when mu is equal to 101, which is a little bit further into that alternative hypothesis space, then how much power are we going to have to detect that the null hypothesis is false and the alternative hypothesis is true? Well, again, we need to evaluate the power function at mu equal to 101. Again, that is given by the probability that z-calc is greater than our critical point, 1.645. But again, that particular representation masks how this 101 participates. But when we use this other representation, we see where it takes part. Now, when we calculate this quantity here, then we get 0.645. And again, we're going to round that to 2 decimal places so that we can look it up in the table. All right, and so notice that when I use that approximation, I'm saying that this probability right here, the probability that the standard normal random variable is greater than 0.645, which is equal to the power that I'm looking for. That is approximately equal to the probability that z is greater than 0.65. So I am acknowledging the fact in these calculations that the value that I'm getting by rounding this z value is approximate. All right, it's not the exact value. And I use that same notation here. You see the dot equal. All right, so I'm stating here very explicitly that the power, for example, in this first part, the power function evaluated at 100.5 is approximately equal to 0.12507. The power of the test when mu is equal to 101 is approximately equal to 0.25785. So we see here that when we move into the alternative hypothesis space a little further, all right, we do increase the power. Our test becomes better able to detect the fact that the null hypothesis is false and that the alternative hypothesis is true. All right, but we still don't have a lot of power. There's only about a 25.8% chance that we would get a hold of a sample that would lead us to correctly conclude that the null hypothesis is false and that the alternative hypothesis is true. And corresponding to that power of 0.25785, we subtract that from 1 to get the operating characteristic function, which is the probability of a type 2 error, when mu is equal to 101, and that is equal to 0.74215. And so there's about a 74.2% chance that the sample that we would obtain would not lead us to reject the null hypothesis. And then finally, for mu equal to 102, we're going even a little bit further into that alternative hypothesis space. What would be the probability of correctly rejecting the null hypothesis? What would be the probability that we would get a hold of a sample that would lead us to reject that null hypothesis? Well, again, we evaluate the power function at that value of mu. All right, and so when we evaluate this quantity here, we get negative 0.355. We're again going to round that to 2 decimal places, and so the power function evaluated at 102 is approximately equal to the probability that z is greater than negative 0.36, and so when we look that up, we get 0.64058. So when mu is equal to 102, then we have about a 64 or 64.1% chance of obtaining a sample that will lead us to correctly reject the null hypothesis and conclude that the alternative hypothesis is true. The probability of a type 2 error when mu is equal to 102 is given by the operating characteristic function evaluated at 102. All right, and we can, because of the relationship between the power function and the operating characteristic function, we can obtain this very easily by subtracting the power from 1. And so the probability of a type 2 error when mu is equal to 102 has decreased down to 0.35942. And so we see here that when mu is equal to 102, there's only about a 35.9% chance of getting a hold of a sample that would lead us to the wrong conclusion. Now that's still a fairly high probability. We may not be comfortable with that, all right, but we do see that what the potential is or the probability is of committing a type 2 error when mu is equal to 102. Now in the next example, we investigate what happens as we increase the sample size and the impact that has on the power of the test and on beta, the probability of committing a type 2 error. So again, let's consider the right-tailed test where the null hypothesis says that mu is less than or equal to 100 versus the alternative hypothesis which says that mu is greater than 100. Again, the population standard deviation is 5. And the test is going to be performed using a significance level of 0.05, 5%. The sample size is denoted by n and varies from 25 up to 75. Now suppose that the true value of mu is 102.5. For each value of n below, compute the power of the test and beta, the probability of committing a type 2 error. All right, so if mu is equal to 102.5, and denoting the sample size by n, the formula for the power of the test is given by this expression here. The power for mu equal to 102.5, and for a given value of n, the sample size, is the probability that a standard normal random variable z is greater than this expression here. All right, so you can see here that n shows up in the denominator of the denominator. And anyway, this simplifies to the probability that the standard normal random variable is greater than 1.645 minus the square root of n, and then that over 2. Okay, so if n is equal to 25, we plug 25 in for the sample size, and we then have to evaluate this expression here, 1.645 minus the square root of 25, divide that square root by 2, and that expression evaluates to negative 0.855. And again, for now, what we're going to do is we're going to round that to 2 decimal places so that it corresponds or matches the precision of the z values given in the standard normal table. And so the power of the test, when mu is equal to 102.5 and when the sample size is 25, that power is approximately given by the probability that the standard normal random variable is greater than negative 0.86. Now, when we look that up in the standard normal table, negative 0.86, all right, so let's scroll up here, negative 0.86, we get 0.80511. Okay, and so what that tells us then is that for a sample of size 25, if in fact the mean of the population is equal to 102.5, then we've got about an 80 to 81% chance of getting a sample that will lead us to correctly determine or discern that the null hypothesis is false and therefore that the alternative hypothesis is true. Another way to think about that, or a corresponding way to think about that, if we are thinking about the probability as a relative frequency type of probability, then we can think in terms of if we were to perform this same experiment from this same population many times, let's 100 times or whatever, then in roughly 80% of those times that we've done it, we would correctly reject the null hypothesis. The probability of a type 2 error is 1 minus the power, and so beta, evaluated at mu equal to 102.5 and n equal to 25, is 1 minus 0.80511, or 0.19489. So there's about a 19.5% chance that we'll get a hold of a sample that will not lead us to reject the null hypothesis, therefore committing a type 2 error if in fact the mean is equal to 102.5. Now if the sample size is 50, then the power of the test is going to be approximately equal to, as you can see here, and I highly recommend that you do these calculations yourself, is going to be approximately equal to the probability that a standard normal random variable is greater than negative 1.89, and that turns out to be, let's see here, 0.97062. All right, and so that's what we have here. So there is about a 97 to 97.1% chance that we will get a sample that will lead us to correctly conclude that the null hypothesis is not true and the alternative is true, if in fact the mean happens to be 102.5. So it's almost assured that when mu is equal to 102.5 and we're using a sample of size 50, we're almost assured of correctly rejecting the null hypothesis. The probability of a type 2 error is only about 2.9%, as you can see here. And then if the sample size is 75, then the power of the test, the probability of rejecting the false null hypothesis, when mu is equal to 102.5 and n is equal to 75, that probability is approximately 0.99643. So only a very, very small chance that we will fail or get a hold of a sample that will, for which we would fail to reject the null hypothesis. And so this test has, for n equal to 75, we've got a lot of power here. Some people might say we have too much power, because remember that having a larger sample size costs more money. It takes more time to gather that much data, to invest the time and the resources to perform an experiment with that many more observations. And so, is it really worth increasing your power by just a few percentage points, well, from 97 up to 99.6%, when you have to, when you would be essentially increasing your sample size by 50%, going from 50 to 75 observations. So that's just a question that one would have to consider in the context of the problem. What the relative cost is for a type 2 error. Compare that to the cost associated with increasing the sample size from 50 to 75 observations, and so forth. So those are just things that the experimenter has to take into consideration when planning an experiment. All right, in the next example, we're going to actually do what's called a sample size question, or sample size determination. So again, consider this right-tailed test, the null hypothesis being that the mean of the population is no more than 100 versus the alternative hypothesis, which says that mu is greater than 100. The population standard deviation is still assumed to be 5 units. Suppose that it's required to perform the test at a significance level of 5%, alpha equal to 0.05, but we also want the probability of a type 2 error to be only 5% as well when mu is equal to 102. So again, notice that we're specifying both the magnitude of the type 1 error, alpha equal to 0.05. So what this is saying is that we're going to conduct the test so that there's only a 5% chance of rejecting the null hypothesis when that null hypothesis is true and should not be rejected. In other words, we're setting up the test so that there's only a 5% chance that a type 1 error is committed. But remember, for a fixed sample size, if we decrease alpha, if we use a smaller significance level, then that's going to increase beta, the probability of a type 2 error. Now, we are in the planning stages of this experiment, and what we're wanting to do is hold not only the probability of a type 1 error, which is alpha, to a fairly small value, 5%, but we also want beta, the probability of a type 2 error, to be 5% as well. And specifically, when mu is equal to 102, we have to be sure that when we specify what we want beta to be, we also indicate at what value of mu that beta is going to correspond to. Because remember, beta is a function of mu. So when mu is 102, we want the probability of a type 2 error to be only 0.05. And so the question is, what sample size is necessary to satisfy these requirements? Now remember that regardless of the sample size, we can specify or set up the test so that alpha is 0.05. But in order to accomplish both or to satisfy that criterion, along with this criterion about beta, we're going to have to make sure that we have an adequate or large enough sample size. And so that's the question. what sample size is necessary to ensure that both alpha and beta are both no more than 5% when mu is equal to 102. And so the goal is to find the sample size n so that the probability of a type 2 error, which again is beta, and we're evaluating this at 102.0, we want that to be equal to 0.05. And so what we have to do is we have to solve this equation for n. Now, this equality will be true if and only if the power of the test is 0.95, right? Beta is equal to 1 minus power. Power is equal to 1 minus beta. And so beta will be 0.05 only, or if and only if power is equal to 0.95. Now, we can either solve this equation for beta for n, or we can solve this equation involving the power for n. And we'll just go ahead and it's a little bit easier to do that in this context to solve the equation for power, or involving power. And so expressing the power function in terms of the standard normal random variable gives us the following equation. 0.95 is equal to the power evaluated at 102.0 and n, where n is the unknown. This is equal to the probability that the standard normal random variable is greater than 1.645 minus 102.0 minus 100 over 5 divided by the square root of the sample size. Now, this expression simplifies to the probability that z is greater than 1.645 minus the square root of the sample size over 2.5. Now, from the standard normal table, we know that the probability that z is greater than negative 1.645 is equal to 0.95. And so we have the two equivalent probability statements. We have the probability that z is greater than 1.645 minus the square root of n over 2.5. That probability has got to be equal to 0.95. And we also know that the probability that z, the standard normal random variable, is greater than negative 1.645, we know that to be 0.95 as well. So we have two probability statements. They both involve z. They both involve z being greater than something. And both probabilities are equal to 0.95. And so what that implies then is that these somethings here must be equal. In other words, 1.645 minus the square root of n over 2.5 must be equal to negative 1.645. And so these two equalities give us the constraint equation that must be satisfied and that we can solve for n. You see, we have one equation and one unknown, the one unknown being being n. And so when we solve this for n, we get n equal to 67.65. Now, since the sample size must be a whole number, we can't have a fractional sample size. The smallest sample size that satisfies the given requirements is n equal to 68. All right? So that is let me go back to the first slide. That is the sample size that will ensure that if we perform this test at a significance level of 0.05, and if in fact mu is equal to 102, then beta will be 0.05 as well. We'll be holding both the probability of a type 1 error and the probability of a type 2 error to no more than 5% if we use a sample size of 68 observations. Now, if mu is greater than 102, then beta would be even smaller, right? Because if mu gets bigger, further into the alternative hypothesis space, then the power is going to go up, and so therefore beta would decrease. Now, the next slide shows how we could approach solving this question graphically as well. So here I have power curves for our right-tailed z-test of a population mean. All right, and we're performing the tests for each of these sample sizes that I've got listed here. We're performing each of those tests at a 0.05 level of significance. Now the sample sizes that I have here are n equal to 9 and 25, 36, 64. Actually, let me see here. No, this is the wrong graph. Let me go ahead and correct this. I'm not sure what LaTeX has done here, but let me fix that and I'll be right back. Okay, I got that fixed. So again, we're doing this sample size determination for a right-tailed test. I've got a number, 1, 2, 3, 4, of sample sizes that I'm considering here. I've got a power curve corresponding to each of those 4 sample sizes. We're performing the right-tailed test at a significance level of 0.05, as you can see here, right? And the null value of the population mean is 100. You can see that, so that's mu sub 0. All right, so that's represented by right here, this vertical line goes through 100. Again, you can see that all 4 of these power curves go through the point 100 and 0.05. All right, because the hypothesized value is 100 and the test is being performed at a significance level of 0.05. Now, for mu equal to 102, we want the power to be 0.95, right? And so what sample size would accomplish that? Well, I've considered 4 sample sizes here. A sample size of 30, right? So that's this power curve right here. A sample size of 50, all right? That's that second curve. A sample size of 70, and then a sample size of 90. And so we can see here, what we need to look at is the intersection of this vertical line at 102 and the horizontal line at 0.95. And we can see here that the curve that comes closest to that and is above it, either at or above that point of intersection, is the curve corresponding to a sample size of 70. All right? And so graphically, we know that we can tell here that the required sample size is about 70. All right? Now, we know that it's actually a little bit smaller than that, but I just wanted to demonstrate how we can actually solve this graphically as well. Okay, now the next thing I want to do is I want to move beyond the tables to more accurate probability calculations using software and calculators. So this applies to power calculations, certainly, but it applies just more generally to calculations involving the normal distribution, and the same kind of thing would apply to calculating probabilities involving other kinds of random variables as well, random variables that follow a t-distribution or a chi-square or an f-distribution and so forth. So in a previous example, we considered the right-tailed test, the null hypothesis of which is that mu is less than or equal to 100 versus the alternative hypothesis that mu is greater than 100, where the population standard deviation is 5 and where the test is to be performed at the 0.05 level of significance using a sample size of 25. So this was perhaps the first example that we looked at. Now, using the standard normal table, we obtained the following value for the power of the test when mu is equal to 102. And so this was the way that we calculated this value for the power. All right, and so remember that one way to represent the power function is to do so using a standard normal random variable, which I've done here. And then we have to evaluate this expression on the right-hand side of the inequality, and that turns out to be negative 0.355. And we discussed that we, at that time, were rounding these values to 2 decimal places to match the precision of the z-values in the standard normal table. So by doing that, we see that the approximate power is, or the power for this test when mu is equal to 102 is approximately 0.64058. All right, so again, this is clearly an approximation because we rounded the actual z-value of negative 0.355 to 2 decimal places, negative 0.36, to match the precision of the z-values in the table. Now, one could obtain a more accurate value for this probability by using, for example, linear interpolation. All right, so for example, we know that the probability that we're after, right here inside the between both inequalities, the probability that z is greater than negative 0.355, we know that that is going to be greater than the probability that z is greater than negative 0.35 and strictly less than the probability that z is greater than negative 0.36. I see I've got a typo here. Perhaps I can fix that for us. Okay, so that's better. So here on the right-hand side, so we know that the probability of interest, the probability that z is greater than negative 0.355 will be not only greater than the probability that z is greater than negative 0.35, but strictly less than the probability that z is greater than negative 0.36. And obviously we could look up both of these bounding probabilities in the z table because those z values are expressed to 2 decimal places. And so doing so, we would find out that the probability that we're after, the probability that the standard normal random variable z is greater than negative 0.355 is greater than 0.63683 and less than 0.64058. All right, now we could take that information and we could perform a linear interpolation to find out or to obtain a better approximation to the probability that we're after. Now, since negative 0.355 is halfway between negative 0.35 and negative 0.36, the interpolated value would be halfway between 0.63683 and 0.64058. So the linear interpolation in this case would be very simple. We would just take the average of those two values. And so that would give us the linear interpolated value for the probability that z is greater than negative 0.355 of being 0.638705. So that is the linear interpolated value. And it turns out that that's going to be it's obviously a better approximation. Turns out that it's really accurate. Okay, we'll come back to that in a few minutes, though. So there are other methods for obtaining more accurate values for such probabilities, including using statistical software such as SAS or Stata or Minitab or SPSS or R, as well as statistical calculators that have the distributions built in. So let's look at an example of how to use some statistical software to calculate power for z-tests and to get very accurate values for power. And so here is the SAS code in the context of a data step, all right, to perform a power calculation for a two-tailed z-test. All right, and so what I'm doing here is creating in this first statement, I am creating a temporary data set, calling it set 1, and then down here at the very end, I'm telling SAS to run everything above it. All right, now the stuff in between the data step and the run statement, all right, this is the contents of the data step, and we're setting up everything that we want SAS to do. So you can see my comments out here. I'm letting alpha be my significance level. I'm setting that to 0.05. I'm using the variable mu, or the variable name mu, to represent the value at which I want to evaluate power, and I'm setting that to 102. Then I have the variable name mu0 for my hypothesized value of mu, and that is being set to 100. Then I've got a variable name called std dev, so for standard deviation, obviously, And that represents my population standard deviation, which in this example is 5. And then I'm setting the sample size to 25 using that variable name. Now, what I'm doing here, the next statement, z equal to probit, and then 1 minus alpha over 2. Probit is a function in SAS, in base SAS, that it looks up a percentage point from a standard normal distribution. And so the value that I need to look up is 1 minus alpha over 2. And so this is actually looking up the percentiles of a standard normal distribution. So if alpha is 0.05, alpha over 2 is 0.025, and 1 minus that would be 0.975. So what this is doing is looking up the 97.5th percentile of the standard normal distribution, and then assigning that value to z. Okay, then z is used in this CDF function. All right, here I've got a negative in front of it, and then I've got z by itself there. And so anyway, what this is doing, it's calling the CDF function in SAS, and the first argument of the CDF function is the name of the distribution to use, and in this case it's the normal distribution. And this is the value at the second argument is the value at which we want to evaluate the CDF. Remember, CDF stands for cumulative distribution function. The next argument is the mean of the distribution, well, in this case, the mean of the normal distribution. All right, so remember that if the null hypothesis is not true, then the value of the mean of zcalc is mu minus mu naught over the standard deviation divided by the square root of n. Okay, and then finally, the last argument is the scale parameter, in this case the standard deviation, and this is 1. Okay, then we add to that 1 minus, and then we're evaluating the CDF function again, but this time instead of evaluating at negative z, we're evaluating it at positive z. And so the power is equal to this expression, and let me show you again where this comes from. So referring back to previous slides, there are actually 2 slides that I'm going to have to refer to, all right? And so again, this is for a two-tailed z-test. We're wanting to calculate the power, and so we have, in general, the CDF evaluated at negative z plus 1 minus the CDF evaluated at z. And this is the expression that we're evaluating, okay? The first term in the sum was the probability that, it was a CDF evaluated at the negative z value, all right? And so that's what this is calculating right here. To that we added 1 minus the CDF evaluated at the positive z value. Well, by the complement rule, that's what this is right here. So when we did these calculations by hand, we used the power formulas that were expressed in terms of the standard normal random variable. But now, in using SAS, and in particular the SAS CDF function, we are going to be implementing the power function expressions that are stated in terms of zcalc actually. Now this is the first slide I wanted to show you. The second slide will show you the rest of where we get the arguments for the CDF function. So going back to where we described the hypotheses that we could test, and then going one slide after that, remember that we said the formula for the test statistic, zcalc, is equal to this expression here, and then we talked about the sampling distribution for zcalc. And in particular, we said that if the alternative hypothesis, if the null hypothesis is, if the alternative hypothesis is true, then zcalc, while it has a normal distribution and a standard deviation of 1, the mean of that distribution is mu minus mu naught over sigma divided by the square root of the sample size. And so that is why we are using this expression right here. And it also shows up right there as well. Okay, and so then once we calculate power, then we can calculate beta by subtracting the power from 1. And then finally, once we have run that data step, then we are going to print out the results using proc print. Now, we have a similar kind of SAS code for calculating the power for a left-tailed test, and I'll let you look through this and make sure that you understand all these statements. And then finally, we have the SAS code for a right-tailed test. So look through this and make sure that you know what these statements are doing. And I would also highly recommend that you copy this code and run it on your own in SAS. Make sure that you can run the program successfully and come up with the values for the power. All right, and you might want to tweak the code here and calculate power for the other examples that we performed when we did it by hand. Now remember that when you do that, you're going to get more exact values for the p-value, or for the power values for the probabilities than we were able to obtain by using the standard normal table, because we were rounding those z-values. So make sure you understand that. Now let's focus specifically on this right-tailed test, because we did perform the right-tailed test by hand. And if we run this, then here is the output that we get from SAS. And so you can see here that we're using an alpha of 0.05 as we specified. The value at which we're evaluating power is 102. The hypothesized value is 100. The standard deviation is set to be 5. And we're using a sample size of 25. Then we get a power equal to 0.63876 and then a corresponding beta of 1 minus that, or 0.36124. Now the one thing that's different here is that the z-value, the critical point, we used 1.645, but SAS is using 1.64485. The reason is because we're asking SAS to give us the more exact z-value, all right, from its built-in functionality, right? It can calculate this very, very precisely. And so because of that, instead of 1.645, it gives us the more correct value of 1.64485. Now, if we wanted to get values that we could, it would be more comparable to what we did by hand, we can just tell SAS to use 1.645 for our critical point z. All right, so that's what I'm doing here. Notice that I've commented out that line. Actually, I wouldn't even have to comment that out if I have this statement after that. All right, and so then when we run this code, we see that it is using a z-value of 1.645. And so when we do that, we get a power which to 5 decimal places is 0.63871. Let's look and see how to do this using a statistical calculator, in particular the TI-84. So here's an image of a TI-84 Plus calculator, and the two buttons that we're going to use to calculate this power, we're going to use, we need to get to the distribution menu, and so what we'll need to do is to press the second key and then the vars button, and that will get us then to this distribution menu. Now the function that we want to invoke is the normal CDF function. That's option number 2 here. And when we press that, we get a wizard that prompts us to fill in the lower endpoint of the interval, the upper endpoint of the interval over which we want to calculate probability, the mean of the distribution, and the standard deviation. Now in using the TI-84 and the normal CDF, what we're going to do here is we're going to use the version of the power expression that involves the standard normal random variable. So you can see here, you'll recall that the value that we computed, the z value was negative 0.355. Now we rounded that to negative 0.36, but we're going to retain here, we want the more exact value, and so we won't round it. We'll just use negative 0.355. Now the upper end point is positive infinity, and the closest thing we can get here on this calculator is this value here. So 1 times 10 to the 99th is what that represents. Okay, and then when we run that, we get a value of 0.63870514448. So we get very high precision for this probability. Now, note that in this situation, the approximation provided by linear interpolation is equal to the exact value rounded to 6 decimal places. In other words, you'll remember, you might want to go back and look in the lecture or the video, that the linear interpolated value was 0.63871. All right. If we round this exact value to 5 decimal places, then we get the same thing, 0.63871. Now, also, if we round, when we rounded to 2 decimal places, all of the values that we've done, we get the same value. Okay, we get 0.64, regardless of which of the methods we use. So the bottom line is, if you need really, really high precision, then you may want to use linear interpolation, or you may want to use SAS software or a calculator like the TI-84. But in many situations, the values provided by the standard normal table will be adequate approximations for all intents and purposes. And so, we can just, use the approach that we used, where we rounded that z value to 2 decimal places and then look that value up in the standard normal table. But when more accurate values are needed, they can be obtained in a variety of ways. For example, linear interpolation of the values in the table, statistical software, and statistical calculators.